We are Biomedical Engineering Senior Design Team 1. This year, we were challenged with redesigning a device for trauma and reconstructive surgeries, specifically used for cable tensioning. Cable tensioning devices are used in combination with cable passers and crimping devices to secure long bone fractures, most frequently occurring in the femur. However, surgeons find that current on-market tensioners add unnecessary complexity to surgeries. Current models cause unwanted crimps in the cable, making rethreading the cable upon retensioning challenging. Surgeons also find them non-intuitive, with multiple locks required throughout the process to maintain accurate tension.
Our team developed a removable handle tensioner that enables efficient single-handed cable tensioning during surgery. Its key innovation, the detachable handle, allows surgeons to tension multiple cables without rethreading, streamlining workflow in the operating room. The handle can be easily removed once the desired tension is achieved, and just as easily reattached if retensioning is needed, which is common with multiple cables. This design also minimizes the impact of cable damage typically seen in current market tensioners. The design process began with initial sketches and 3D modeling done in SolidWorks. These models enabled us to 3D print prototypes in resin for early testing, which revealed key areas for improvement. Due to the brittle nature of resin, we found that the removable back handle was the first component to fail. To allow for more effective testing of the device's vital components, we integrated the back handle into the main body of the device. To illustrate the device's appearance with the handles removed, we produced additional prototypes without the back handle.
To ensure the device would be able to meet the objective tension requirement of 500 newtons, we did testing at Resolve Surgical with our resin models. We chose to highlight a torque versus tension test and an applied load to failure test to fully demonstrate the capabilities of the device. As you can see on the graph, the resin device was able to output 398 newtons of force with a torque of 90.6 inch-pounds. In the next test, the device maintained a rising load up to 1,814 newtons before fracturing. These tests show that the device will be able to produce a tension of 500 newtons without fracturing when they are made out of stainless steel. In preliminary testing, participants found the device to be highly intuitive, easy to feed cable through, and operable by users with varying grip strengths. This makes the removable handle device better suited for surgical settings, offering a more user-friendly and reliable device for reconstructive surgeries.
Future design implementations that we believe would further push our prototype to a finalized product would be the implementation of a scale to the front of the device to relay tension measurements, redesigning the handles to allow them to attach and detach together, implementing a return to the front handle for ease of use, incorporating a bearing for the ratchet to reduce friction wear on the device, and scale down the whole device to allow more space for multiple devices during a single procedure.
This removable handle device prioritizes efficiency and usability by addressing clinical challenges reported by surgeons in trauma and reconstructive surgeries. We would like to extend a thank you to our sponsor, Resolve Surgical, for all their input and for allowing us to work on this project with them, as well as thanking our biomedical engineering advisors, Dr. Han and Dr. Lee, for their expertise and guidance throughout our design process. We would also like to extend our thanks to Russell Stein for his help with metal printing, Dr. Jang for his help with mechanical analysis, and Dr. Kirkpatrick and the entire biomedical department for their continued support and guidance.